Okay, so I want to discuss scaling of a random variable. So let x be a random variable, let mu be the expected value of x, and let sigma be the variance of x. Now notice a few properties of the variance, just to remind ourselves, that if I take the variance of a times x plus b, that's quite simply the variance of a squared times the variance of x. So in other words, the b disappears, and a comes out as a squared. And if we define the standard deviation of x to be the square root of the variance, which is always positive, then the standard deviation of ax plus b, it's not hard to see, is just the absolute value of a times the standard deviation of x. Alright, now with that in mind, let's see what happens if I take any random variable and I define a new random variable as x star, so that's a new random variable, is defined as x minus mu, the mean of x, minus its standard deviation, right? Because the standard deviation is the square root, which is just sigma. Now I claim that x star has mean 0 and variance or standard deviation equal to 1. Of course, if the variance is 1, the standard deviation is also equal to 1 because it's just the square root. So let's see if that's true. So x star is just equal to the expectation of x minus mu over sigma, which is equal to the expectation 1 over sigma times the expectation of x minus mu. The expectation of x is just mu, so this whole thing is equal to 0. Similarly, if I write the variance of x star, that's equal to the variance of 1 over sigma times x minus mu over sigma. And if we just use this property here, we can pull this out and we get it squared, sigma squared, the variance of x, and this doesn't matter. And since the variance of x was sigma squared, this is just 1. So this is what's called a standardized, this is called standardizing x. So in other words, you shift it so that it has mean 0, and you rescale it so that it has variance 1. Alright, so that's one important idea, and now let me make one more calculation. So now, what we're interested in is what happens if I have a number of independent random variables. So now let's let x and y be two random variables, and y and x independent. Okay, let them be independent. Then, an important fact is that the variance of x plus y is equal to the variance of x plus the variance of y. Now that's a very simple statement, but it's only true if they're independent. Now, in general, it's always true that the expectation of x plus y is the expectation of x plus the expectation of y. So it's always true that the means, the expected values add, but the fact that the variance adds only happens when they're independent. And to see this, let's let mu be the expected value of x, and let's let nu be the expected value of y. Then the variance, then we can write x plus y. We can write that as x minus mu plus y minus nu plus mu plus nu. Okay, I've just added and subtracted these. And now if I calculate the variance of x plus y, now adding a constant doesn't change the variance, so that's the same as the variance of x minus mu plus the variance of y minus mu, of y minus nu. Okay? so we get that's true. So now we're left just to calculate the variance of this sum here. Alright, so now how do we calculate the variance of that? Well, the variance of this is, the first thing we do is we take the expected value of the quantity here squared, so I'm going to write that as x minus mu plus y minus mu, y minus nu, and this whole quantity squared sorry, yes, it's just this whole quantity squared, that's right. And why is that? Normally we would subtract off the mean, but each of these now have mean 0. So I've subtracted off the mean before I squared it, but the mean of this term and the mean of that term are both 0. So now if I just multiply this out, I end up with the expected value of x minus mu squared plus the expected value of y minus mu, y minus nu squared, and then I'm left with the cross term, 2 times the expectation of x minus mu, y minus nu. Okay, so the first term, just continuing here, the first term, the expected value of this is just the variance of x minus mu. And this term is just the variance of y minus mu. And now this term, since these are independent, this is just the expected value of x minus mu times the expected value of y minus nu. But both of these are equal to 0 because the expected value of x minus mu is the expected value of x minus mu, but the expected value of x is just mu. So those are 0. And so lastly, since adding or subtracting a constant, should have been a nu, doesn't matter, this is just the variance of x plus the variance of y. Alright, so how are we going to use this new fact that we've just shown? Let's use it in an interesting way to prove something which will be useful for us later. If I define x bar n to be 1 over n, the sum xi, I equals 1 to n, with xi, iid random variables with expected value xi equal mu and variance xi equals sigma squared. So these are independent, identically distributed random variables. So they have the same mean and variance since they're identically distributed, and we'll call that mu and call that sigma. So I is just a dummy variable here. Now it's useful to ask ourselves, well, what's the mean of x bar? So x bar is just the average of these n independent random variables. Well, the expected value of x bar n is just 1 over n, the sum I equals 1 to n, the expectation of xi. Now the expectation of xi is just mu, so I have mu for every term here. I have n terms, so the sum is just n times mu, and then I divide, so it's n times mu, but I'm dividing by n, so the answer is just mu. And very similarly, if I look at the variance of x bar n, well, that should be the sum of the variances. So, because they're independent. So first, let's pull out the factor. So that's the variance, 1 over n, the sum I equals 1 to n xi. And now I'm going to pull out the n, and then when you pull a constant out through a variance, it becomes squared. And now, since these are independent, so I have now just variance of the sum I equals 1 to n xi. But since these are independent, this is just the sum of the variance. So that's 1 over n squared the sum I equals 1 to n of the variance of xi. Now for each xi, this is sigma squared. Again, I have n terms, so I have n times sigma squared, just like before, but now I have n squared in the bottom. So notice this turns into sigma squared over n. So in particular, we conclude that the expected value of x bar of n is equal to mu, but the variance of x bar n is equal to sigma squared over n, and the standard deviation, which is just the square root of this, is equal to sigma over square root of n. So notice as n gets very big, the mean stays the right number, it stays what it should be, the average, but the variance decreases. So the fluctuations, how much this deviates from its mean, is going to 0. Okay, thank you very much.